Hello everyone, welcome to NA's Institute, a complete chemistry classroom program. In this class, we will learn about ferredoxin, mainly what are the ferredoxins, that is the definition of ferredoxins, then different type of ferredoxins we will come to know and how they will be formulated, and finally we will look into the biofunctions of these kind of ferredoxins. First of all, we'll have to know from where the ferredoxin term has been developed. So now if we divide this term into two parts, so it will we will get that fer and redoxin, right? So fer means basically iron and redoxin means basically redox protein. Why fer means iron? Because see that in many cases iron has been named as ferrous or ferrite, and in next part redoxin means redox protein. So basically a redox protein in which iron atom is present, and you can say that the redox protein may show or should show some kind of oxidation and reduction reactions simultaneously. So what are the main uses of ferredoxin? So far we have come to know that ferredoxin is one kind of redox protein. So redox protein means that in that protein the redox reaction is going on, or some kind of oxidation and reduction reactions are going on simultaneously. So basically the electron process, that we are getting some kind of electron transport process. So mainly the ferredoxins are used in biological electron transfer process like photosynthesis, nitrogen fixation, etc. So if you like to have a definition of ferredoxin, we can say that ferredoxins are non-hemi-iron sulfur proteins characterized by the presence of polymetallic system containing sulfide ions, and the iron ions will have some kind of variable oxidation states. Why the iron ions will have variable oxidation states? Because see that we have already come to know ferredoxins are one kind of redox protein. So redox protein means that we here we will get some kind of redox reactions or some kind of oxidation and reduction reactions simultaneously. So basically in order to maintain that, or in order to follow that, the iron ions will have to have some kind of variable oxidation states. So in the definition of these ferredoxin, we have mentioned that ferredoxin is one kind of non-hemi-iron sulfur protein, right? So prior to move to the next part of this class, we have to clear our doubt that what are the basic differences between these non-hemi and hemi-iron, right? So basically iron from food comes into two forms. One is hemi and another form is non-hemi. Hemi is mainly found in animal flesh like meat, poultry and seafood, whereas non-hemi iron is found in plant foods like whole grains, nuts, seeds, or you can say that leafy greens. And the non-hemi iron is also found in animal flesh, as animals consume plant foods with non-hemi iron and fortified foods. Here again I want to repeat that ferredoxin is one kind of non-hemi-iron sulfur protein, and if we divide this term into two parts, we will get fer and redoxin. Fer means iron and redoxin means redox protein. And this ferredoxin is generally abbreviated as FD, that is capital F and small d, and it is actually universally accepted. Here we will discuss some important properties of this ferredoxin. See, these ferredoxins are extremely important in many biological electron transfer process. Why? Because they are always available in all kind of living bodies, and they play very much vital roles in photosynthesis, mitochondrial respiration, nitrogen fixation, etc. Ferredoxins mainly act as electron transport proteins in many biological redox reactions. Redox reactions means that the oxidation and reduction reactions occur simultaneously. And in these iron sulfur proteins, or you can say that non-hemi iron sulfur proteins, both the cystenyl sulfur and inorganic sulfur as sulfides are present. So what are the basic differences between the cystenyl and inorganic sulfurs? See that cystenyl sulfur means you can say that these kind of sulfur are organic sulfurs, or here the protein chain will be linked, whereas in case of inorganic sulfur you can say that these kind of sulfurs are directly bonded with the metal ion. So the inorganic sulfurs are labile, Why they are labile? Because see that in case of inorganic sulfurs, they are mainly ionic, because see that they are directly attached with the metal ion. So the metal will be positive and the sulfur will exist as sulfide, and they can be easily removed as H2S on acidification, and hence therefore they will be labile in nature, whereas the cysteine sulfur cannot exist as sulfide, so they are comparatively stable in nature. So continuing the properties of ferredoxins. The iron sulfur proteins are very often represented as small n Fe and then small ms. So the small n denotes the number of iron cations per protein molecule. It doesn't mean the total number of iron cations in the whole protein chain. It does only mean that the total number of iron cations per protein molecule. And these M denotes, the S denotes the labile sulfur. S doesn't denote that all kind of sulfur, that is the cysteine or inorganic sulfur. So S denotes only the labile sulfur, or you can say that only the inorganic sulfurs. And M denotes the number of labile sulfur sites. So M means that only the sulfurs which will be labile in nature. M doesn't mean that the total number of sulfur site presents in the protein molecule. Only the sulfurs which are labile in nature, only the sulfurs which will be inorganic in nature, that is basically represented by the term small m, and that is basically per protein molecule, not for the whole chain. It is only for the protein molecule. It is only per protein molecule. Coming to the next point, in all iron sulfur proteins, or in these all iron sulfur proteins, Fe or iron is actually positively charged, or it is having some kind of variable oxidation states, and it is approximately tetrahedrally surrounded by the sulfur sides, but at least one of the side is cysteine sulfur, at least, because as it is tetrahedrally surrounded by the sulfur sides, so there will be 4 sulfur sides around iron ion. So at least one among the 4 sulfur sides would be cysteine sulfur, otherwise it will not be called as ferredoxin. In the electron transport process, the Fe3 plus by Fe2 plus couple works, and both the oxidized and reduced forms of iron remain in high spin tetrahedral geometry. See that as the redox reaction we are expecting in these kind of non-hemic iron sulfur protein, so therefore the iron will have variable oxidation states, and as the plus 2 and plus 3 oxidation states are stable in case of iron, so therefore in these cases we are getting Fe3 plus by Fe2 plus couple as a working couple. But see that in these both oxidized and reduced form, iron remain in high spin tetrahedral geometry. Why? Because see, as we have already come to know that around iron there is one kind of tetrahedral coordination. So for this tetrahedral case, we know that octahedral splitting is much more than the tetrahedral splitting. And again the iron is binded with the sulfur sides, and we know that sulfur is actually weak field ligand. So due to these two reasons, that is, first one is the tetrahedral splitting compared to octahedral splitting. Tetrahedral splitting is comparatively less, and second is that sulfur is actually a weak field ligand. So due to these two reasons, actually the overall splitting will be less, and as the overall splitting will be less, then it will undergo a high spin tetrahedral geometry. Again, the sulfur binding sides are relatively soft, and therefore it will try to stabilize the lower oxidation state, that is the plus 2 oxidation state of iron, among the plus 3 and plus 3 oxidation states. And finally, the ionic radii of these tetrahedral high spin iron plus 3 or iron plus 2 will not be same, and actually it will differ, and therefore the tetrahedral geometry around the iron atom will be not a particular or will be not a perfect tetrahedral one, rather than it will be a distorted one. Now we will learn different types of ferredoxins, and we will mainly look into the main types. So first one is the 2Fe2S, that is 2 iron ferredoxin, and it is also designated as Fe2S2 protein. And Fe2S2 protein means that two iron atoms or two iron ions are actually present per protein molecule, whereas two sulfurs are present per protein molecule, and those two sulfurs will be the inorganic sulfur. We are not commenting about the number of sulfurs which are actually the cystenyl one, which are we are only commenting, or which are only designating the number of inorganic sulfurs or the labile sulfurs. And it is a binuclear moiety. Why it is a binuclear moiety? See that as it is designated as Fe2S2, so per protein molecule two metal ions are present, so therefore we are designating it as a binuclear moiety, because per protein molecule it will have two iron ion with two bridging inorganic sulfurs. So when we will just look into the structure, then we will come to know why it is called as the binuclear moiety with two bridging inorganic sulfurs. Now coming to the next point, there are two iron centers, but it acts as a one electron transfer agent. See that there are two iron atoms, right? So now if the oxidized state will have two iron atoms as +3 oxidation state, and if the reduced state is having the oxidation number of +2, then see when it will undergo from oxidized to reduced state, then there would be two electron transfer process. But see that it is actually a one electron transfer agent. So the oxidized form, or in the oxidized form, both the iron atoms are actually in +3 oxidation state, whereas in the reduced form both the iron atoms cannot be in +2 oxidation state. One is in +2 oxidation state and another one is in +3 oxidation state, in order to follow just the one electron transfer process, or in order to maintain it as one electron transfer agent. Now, in both the oxidized and reduced forms, each iron center remains in high spin state in a distorted tetrahedral geometry. Why distorted? These things we have already discussed in previous slides, that iron is in +3 and +2 oxidation states in different oxidized and reduced form, but the size of these +2 and +3 oxidation states iron will differ in nature, and therefore the tetrahedral arrangement around the iron atom will not be a perfect one, rather than it will be a distorted one. And why the high spin? See that the tetrahedral splitting will be very much less, or the value of these tetrahedral splitting is very much less compared to the octahedral splitting. And again the iron atom is bind with these sulfur sides, and we know that sulfur sides are actually the weak field ligand. So because of these two reasons, the total tetrahedral splitting will be less in nature, and therefore it will be high spin, or it will show a high spin tetrahedral distorted geometry. Now the diamagnetism in the oxidized form arises through the anti-bonding, through the anti-ferromagnetic coupling, that is the super exchange phenomena. Now if we just calculate the total number of electrons present in the iron +3 oxidation state, then we will come to note that there will be total 5 electrons. Now if it will be high spin in nature in the tetrahedral coordination, then we will come to know that the electronic configuration will be E2T23 with high spin nature. But see that if we are just assuming that assuming it as one iron ion, then it would be paramagnetic in nature. But you have to know, or you have to point out, that there are actually two iron atoms which are actually bridged by the sulfur ligands. So basically individual iron is actually paramagnetic, but in overall structure these two irons are undergoing the anti-ferromagnetic coupling through the super exchange mechanism, and therefore all these electrons will be paired up to show a diamagnetic character, and these pairing up is actually occurring via the bridging sulfur sites. So therefore it is the super exchange phenomena, or you can mention, or you can call it as the anti-ferromagnetic coupling. Whereas in the reduced state, that is the iron +2 oxidation state, and another iron will be in +3 oxidation state. So there will be, in one iron there will be total 6 electrons, and in another iron there will be total 5 electrons. Even in this case, if the super exchange phenomena or the super exchange mechanism will play, or will just occur, or the anti-ferromagnetic coupling will occur, even in that case also one electron will be unpaired, because see, all over there will be total 11 electrons, so max there 10 electrons will be paired up, but at least one electron will be unpaired, and these results into a paramagnetic state. Why? Because see, that paramagnetism means that there will be at least one unpaired electron, and here in the reduced state we are getting one unpaired electron with spin equals to plus half, and therefore if you are just calculating the total spin multiplicity, then there will be 2s plus 1, so it would be total 2, and hence it is named as doublet paramagnetic state. So the total 10 electrons will be paired up through the super exchange mechanism, or you can say it as the antiferromagnetic coupling, but there is actually total 11 electrons, so one electron will be unpaired, which results in it into a paramagnetic state, that is a doublet paramagnetic state due to the spin multiplicity equals to 2. Thus, in the reduced state, the metal centers are not equivalent. Why the metal centers are not equivalent? Because one metal ion is in plus 2 oxidation state, whereas the other metal ion is in the plus 3 oxidation state. Whereas in the oxidized form, both the metal ions are equivalent because both the iron ions are in plus 3 oxidation state, and due to which it is acting as a 1 electron transport protein. Here just look at the structure of these two Fe-ferredoxin. Here two iron atoms are present of variable oxidation states, which I haven't mentioned the oxidation states of these iron atoms because I just wanted to give you a general representation of these two iron ferredoxin or two Fe-ferredoxin. So here are two iron ions, or which are actually bridged by the two sulfur atoms. These sulfur sites are actually inorganic sulfur. These bridging sulfurs are actually the inorganic sulfurs, and see that there are 4 cystenyl sulfurs, and the irons are actually tetrahedrally surrounded by the sulfur sites. Among these 4 sulfur sites, 2 are cystenyl and 2 are bridged inorganic sulfurs. Now try to understand the electron transfer process of these two iron ferredoxins. See the first structure is of the oxidized form. Here the two iron ions are in plus 3 oxidation state, and there are 2 bridging sulfurs and 4 cystenyl sulfurs. Now these oxidized forms are being converted into a reduced form by gaining 1 electron, and in the reduced state see that there is one iron in plus 3 oxidation state, and the other iron is in plus 2 oxidation state, and the all over charge would be 3 minus as it is a reduced state. See that as the oxidation state of one iron is reduced by 1 unit, so therefore the total charge or the all over charge of the species would be 3 minus, right? So this is the overall electron transfer process, and just below that I have just again wanted to give you a general representation of the structure of of the active site of these two iron ferredoxin, and this is basically the reduced form of these two iron ferredoxin. The representation is basically the active site of the reduced form of 2 iron ferredoxin. It is another type of ferredoxin, and it is named as Rieske center. Now it does also belong to the same class, that is 2Fe2S ferredoxin. But there is one basic difference between these 2Fe ferredoxin and this Rieske center, and it is that in Rieske center at least one cystenyl binding site should be replaced by the imidazole N site of histidine residues. So that is the overall difference, or that is the basic difference between these 2Fe ferredoxin and Rieske center. That is the structural difference. So there is no major difference between these two ferredoxins, and ligation of these non-sulfur binding sites remarkably influence the reduction potentials of the Fe3 plus by Fe2 plus couple. See that in the 2Fe ferredoxin the coordination sites were 2 cystenyl sulfurs and 2 inorganic sulfurs, but in this Rieske center one of that cystenyl sites will be replaced by the imidazole N sides of histidine residues, right? So because of this nature, that because of these non-sulfur binding sites which is attached with the iron, because of the change of the environment surrounding the iron, the reduction potential of the Fe3 plus by Fe2 plus couple will be changed a bit, but the overall procedure or the other properties of these Rieske center or these kind of ferredoxin will be almost similar to that of 2Fe ferredoxin. Okay, just here try to look at the structure of this Rieske center. See that the two iron ions are present and two sulfur bridging sites are also present, and in the right side actually two cysteine sulfurs are being replaced by these N-histidine or imidazole N-histidine residues, right? And there is one protein chain surrounding of this structure. Okay, so therefore this is the overall representation of Rieske iron sulfur center. Here I have also here I didn't mention the oxidation state of iron. Why? Because I just wanted to show you a general representation of this Rieske center. So now if it will be oxidized form, so then in that case the oxidation state of these two iron atoms will be +3. Now if you want to draw the structure of a reduced form of this Rieske protein or the Rieske structure, then one iron atom will be in +2 oxidation state and one iron atom will be in the +3 oxidation state. Okay, so but the other properties would be almost similar to that of 2-Fe ferredoxin. Here it is the general representation of a Rieske iron sulfur center. So there are two iron ions, then in the middle there are two inorganic sulfurs or the labile sulfurs, and they are mainly bridging sulfurs. In the left hand side there are two cysteine sulfur sites, and in the right hand side two cysteine sulfurs are being replaced by two N-imidazole histidine residues. Now see that here the protein chain is not shown, but in exam you have to draw the protein chain surrounding this active structure. So you will have to draw the protein chain. Okay. So here it is another type of ferredoxin, and it is designated as 4Fe4As or 4Fe ferredoxin. So 4Fe ferredoxin or 4Fe4As ferredoxin means that there are 4 iron atoms per protein molecule, and here also 4 labile or 4 inorganic sulfur sites are present. 4S doesn't mean the total number of sulfur sites including cysteine and inorganic. So 4S does only mean that there are only 4 labile or 4 inorganic sulfurs. So in each unit it is a Cuban-like cluster of 4 iron centers in which each iron center is coordinated by a cysteine residue, and other 3 sides are occupied by 3 labile S sites or 3 labile sulfur sites. So each iron center will be surrounded by 1 cysteine sulfur sites and then 3 inorganic sulfur sites. So therefore this tetrahedral coordination will be achieved. So in this structure, whatever it is shown in the slide, here the protein chain is not shown, so you have to draw it like this, that the protein chain should be surrounded to this active structure. So here we will try to learn the electron transfer process of this 4Fe4S cluster or the 4Fe ferredoxin. So in these 4Fe ferredoxin, in the oxidized form, the iron atoms will be in variable oxidation state. 2 iron atoms will be in +3 oxidation state and 2 iron atoms will be in +2 oxidation state. And in order to follow it as one electron transfer agent, the reduced form will be, or in the reduced form, not all the iron atoms will be in +2 oxidation state. So there will be at least 1 iron atoms will be in +3 oxidation state and 3 iron atoms will be in +2 oxidation states, and therefore it will follow as one electron transfer agent. So in the oxidized form, see that the total number of electrons would be even, right? So if you will undergo an antiferromagnetic coupling or super exchange phenomena, whatever we have already discussed in the last few slides, so through that kind of mechanism it would be antiferromagnetic, it would undergo antiferromagnetic coupling, and therefore it would be diamagnetic in nature. But when you will consider the reduced state, then see that the total number of electrons, including this 1 iron in +2 oxidation state and 3 iron in +2 oxidation state, so that will not be a even number. So ultimately that will be paramagnetic in nature due to the presence of one unpaired electron, and the total spin will be +half, and therefore it will be paramagnetic in nature. And see that the electron transfer process will be like this, that 2 iron atoms are present in the oxidized state, that is 2 in +3 oxidation state and 2 in +2 oxidation state, and it will be converted into the reduced form where 1 iron is present in +3 oxidation state and 2 iron and 3 irons are present in +2 oxidation state. Herewith, I want to mention that in these 4AP ferredoxin, we have already come to know that the two iron atoms will be in different oxidation state or will be in variable oxidation state in oxidized as well as in the reduced form. But the experimental evidences indicate that the four iron centers are equivalent with some average oxidation state. Why this is happening? See that in these kind of 4AP ferredoxin, the electron transfer process is going on and it is becoming very fast, that all over the experimental evidences indicate that the four iron centers are equivalent, so they cannot separate the four iron atoms based on the oxidation state, so all the iron centers becomes equivalent in nature with the average oxidation state. And these equivalent character indicates an extensive delocalization within the clusters, that the plus 3 and plus 2 oxidation state of these iron atoms, or the different kinds of variable oxidation states of this kind of iron atoms, so therefore the electrons will be delocalized within the cluster, and thus the plus 3 or plus 2 iron atoms will not be separated at all, and they will be equivalent in nature. And now here I want to mention, or I want to point out one special type of these four iron clusters, which is known as high potential iron proteins. It is also one kind of 4-Fe ferredoxin, but it is actually acting as high potential iron proteins. Why? Because of the structure, because of the difference in their structure. It is also a 1 electron transport protein, but the corresponding reduction potential is very high. In these high potential iron proteins, mainly the oxidized form is consisting 3 iron atoms with a plus 3 oxidation state, whereas 1 iron atom with plus 2 oxidation state, and it becomes paramagnetic in nature due to the presence of 1 odd electron or 1 unpaired electron, whereas the reduced form is having 2 iron atoms in plus 3 oxidation state and 2 iron atoms will be in plus 2 oxidation state, and it will be diamagnetic in nature due to the super exchange phenomena or antiferromagnetic coupling. But see, the overall structure is somehow different from the conventional that 4-AP ferredoxin, whichever we have already learned in the last slide. So therefore, due to the difference of its structure, it is named as high potential iron proteins, because of having higher potential or higher reduction potential than the previous one. Now look at the electron transfer process of these special type of 4-EP ferredoxin, that is the high potential iron protein, where the oxidized form is consisting 3 iron in plus 3 oxidation state and 1 iron is in plus 2 oxidation state, and it will be converted into a reduced state, which is actually diamagnetic in nature, where 2 iron atoms will be in plus 2 oxidation state and 2 iron atoms will be in plus 3 oxidation state. So we have already learned 2-Fe ferredoxin, that 2Fe2As, then Rieske center, then we have already learned these 4Fe4As ferredoxin or 4-Fe ferredoxin. But see that the ferredoxin is not limited only to these three types. There are various types of ferredoxins, but we are mainly considering the main types. So other common types are that 3Fe4As ferredoxin or 8Fe8As ferredoxin. And herewith I wanted to show you the structure of these 3Fe4As ferredoxin, which is actually reflected on your screen. So these are the main biofunctions of ferredoxins, or you can say that what kind of usage of ferredoxins. So ferredoxins play a vital role in these electron transfer in many biological processes like photosynthesis, nitrogen fixation, etc., whichever we have already discussed. There is one kind of ferredoxin, that is 2-Fe ferredoxin, and it is mainly involved in both cyclic and non-cyclic photophosphorylation reactions of photosynthesis. And there is another type of ferredoxin which we have already learned in the last last few slides, that is 4-Fe ferredoxin, and it is actually a 1 electron transfer ferredoxin, or it can act as a 1 electron carrier in photosynthesis and in the activity of nitrogenase, etc. And it is actually originally found in bacteria, and therefore it is known as bacterial type ferredoxins. Mainly the 4-Fe ferredoxin is named as bacterial type of ferredoxins. Here I have just shown you a general table of different main types of ferredoxin, like these 2-iron ferredoxin, 3-iron ferredoxin, 4-iron ferredoxin, and their clusters, how their clusters looks like, that is 2Fe2As or 3Fe4As or 4Fe4As, and their oxidized and reduced form, how the oxidized form is written, how the reduced form is written in different cases. So you can look into these for a more clear picture. So I think that your doubts will be much more cleared through this table. So thank you for today's class. In this class, we have already learned what are ferredoxins, the basic definitions of ferredoxins, then from where the term has been developed, what are the basic uses, what are its biofunctions, what are its roles, and then different types of these kind of ferredoxins and their mechanistic action, their structures. Okay, so once again, thank you for watching this video, and if you have any doubt regarding this class, you can directly contact us through the website www.nsinst.com, or you can drop a mail at nsinst@gmail.com, or you can directly call, message, or WhatsApp us in the given number. Once again, thank you. See you in the next class.